Hello and welcome back. Today we're going to review Unit 13, Statistics. I'm going to break this review into two separate videos. The first video I want to focus on the descriptive statistics, the very basics about statistics, and in the second video we're going to focus on the inferential aspect of statistics. And there'll be lots of examples in the second video of how to apply the inferential statistics. Here's an overview of the lessons that we learned. Just recall that lessons 8 through 10 were actually additional lessons provided to us to help supplement the unit by Mr. Weiler, which meant that the old 8 and 9 got changed to 11 and 12. Okay, so just note that. As with the previous review videos, I want to provide the Common Core standards associated with Units 13. Now these are the standards that are going to be used to create the Regents exam questions, so it's a good idea just to pause the video now, get a sense for what you're going to be expected to do. Okay, here's another set of Common Core standards, so pause again the video to just make sense of these standards as well. So let's get right into it. Okay. There are several formulas that we learned in this unit. The first one is the z-score formula. Now, in general, the z-score formula is a way that you can calculate the number of deviations a value is from the mean. Okay. And we looked at z-scores in relation to data values. We looked at them in relation to sample means and to sample proportions. But the general idea is the same. The z-score is always taking whatever you're looking to find the z-score of, which is the data value in this case, minus the mean you're comparing it to, divided by the standard deviation. Now you might see it with the sample mean and the sample deviation. So again, you might see it listed like this, x minus x bar over the sample deviation s. But notice it's essentially the same formula. Dealing with the z-score for sample means, it's going to be x bar, the sample mean that you're wanting to find the z-score for, minus the mean of the means, mean of all the x bars, divided by the standard deviations of all the means. And note that this mean of the means, that's equivalent to the mean of the population. So if you're testing the mean of the population, or against the mean of the population, you're going to use mu from the population. That is the same as the mean of the means. And the other form for the z-score was dealing with sample proportions, and that dealt with p-hats. The p-hat, you want to compare it against the mean of the p-hats, which, by the way, again, is equal to the population proportion, divided by the deviation of the sample proportions. And there were formulas for the deviation of the sample means and the deviation of the sample proportions, which are going to be listed next. The deviation of the sample means is found by taking the deviation of the population divided by the square root of the sample size. Now, the larger your sample, the smaller your deviations of the means are going to be, because you're going to be dividing by a larger number. Now, there were some times where we didn't know the deviation of the population, so you might use the sample deviation instead. And it's going to be an approximate value for the deviation of the population. It's not going to be exact, but it'll be close enough that you're going to use that in some instances. It'll still work just fine. The deviation of the sample proportions was found using the formula, the square root of the proportion you're essentially testing times 1 minus the proportion, so the complement, all over n. So those are the main formulas that we use in the statistics unit. So pause the video and make sure you have these written down. Now I want to take a moment just to talk about the different types of variability that occurred. Because when you're dealing with a statistical situation, there's always some kind of variability that's involved. Okay? And there's different types. The first one we went over was called observational or measurement variability. And that just occurs just due to the fact that measuring instruments are not going to be precise enough. Okay? Or it could occur because two different people read a different measurement. So a common example is, if you want to see how long it takes for something to happen, one person might say it says 7.3 seconds from their perspective, another person might say 7.2 seconds. Okay. That variability occurs because of measurement variability. Natural variability occurs whenever members of the population, due to the fact that everyone's different, okay, natural variability is going to occur. So for instance, if you are doing some kind of a study to see the effect of a pill, a certain medical pill, a weight loss pill, some people lose weight faster than others. It's just due to their own natural bodies. Okay, everyone has a different natural being. Okay. So that kind of variability could occur. Induced variability occurs when you kind of force some variability. Okay, when you force different outcomes, and that really occurs whenever you have experimental. Okay. Any kind of an experimental study has induced variability built into it. Okay, basically, when one group is treated differently than the others. And one group would have the medical pill that's being tested. Spell being right. Being tested. So that's group 1. Okay, and the group 1, and group 2 will be given something called maybe a placebo. Okay, which is essentially just like a fake pill. And the whole point of this is, so that the people who are being studied have no idea if they have the real pill or not. Okay, so you're inducing some variability in that situation. You're creating variability because you want to see the effectiveness of the medical pill, see if it works or not. And the last type of variability is the sampling variability. And that just occurs whenever you take random samples from a population. People are going to give different responses. People are going to have different opinions. Okay, that's sampling variability. Now let's look at reviewing the different types of obtaining data. There are three main ways we looked at. The first way was a survey, and that's one of the most common ways that you see people obtain data. You fill out a survey, and you give your responses, and someone takes the survey, and they compound the data, and they make some analyses about the data from the survey. Okay, but it's just collections of data from a population where the variability is not induced. You just want to find out, in general, something about the sample itself. An observational study and an experimental study are very similar to each other. The differences between these two studies is that in observation, the people from the population are not under the control of those performing the study. Okay, the assignment into treatment groups is not under the control. So you're looking at something that already occurred, and you're kind of separating them into different groups. Okay, just to see what kind of results you can get from different groups. Okay, you have no hands in the situation. You're just basically observing the data. An experimental study is where the assignment of individuals and the control is under the control of the people performing the study. Okay, so this is where you split specifically into two groups of people, where one group of people has a certain set of conditions and another group of people have a different set of conditions, and you want to see what happens. So you actually do have some kind of say in the study itself. All right, pause the video, write down any notes that you want to before moving on. Now, another thing I want to touch upon are the different notations that we saw, because it's very easy to confuse the different notations that we have and what they're referring to and what they're not referring to. In general, we have two different categories. We have values from the population, okay, which are called parameters, and we have variables and values from the sample, which are called statistics. Okay. Now, in real life, you don't know the parameters values. You don't know the population values. Okay, so what we do is we collect samples and we look at the statistics to help infer something about the parameters. But there are different notations referring to values referring to the population, values from the sample. Okay? And the first one is the mean. The mean of a population is denoted as mu. For a sample, the mean is denoted as x bar. Same concept, just different notation. One refers to the population, one refers to the sample. Now notice every population has only one value possible. Okay? The mean for the population, because it counts for everyone, is going to be the same value no matter what. But a sample, you're going to get different values. Okay? So that's why it's important to note the differences between these two things. Okay? A sample from the population could have the same value as the population, but it will most likely have something slightly different. A proportion from the population is denoted as p, whereas from the sample, it's denoted as p hat. The hat over there typically means it's the predicted value. That's sometimes what people refer to it as, a predicted proportion. Okay. The standard deviation from a population is sigma, the Greek letter sigma. Sometimes people draw it like this. Okay. Depending on how you are in your writing, I like to do it this way because it's a little easier to draw that figure. It means the same thing, okay? But it's sigma. But for the sample, you just have an S. That just stands for the sample deviation. Sometimes you'll see a little X afterwards. Sometimes you'll see a little X bar or P hat afterwards, but those are below, and we'll see that in a moment. Okay. The mean of the means, okay, it deals with mu, but we're going to be dealing with the mean of the means of sample means. Okay, so this is what that notation looks like: the mean of all the sample means. So in a sense, it is a population parameter, but it's based upon sample size. It's based upon the population itself, okay, and the sample means that are distributed. Okay. Deviation of the means, there's a formula we saw for that in the previous slide. Okay, that's what that looks like. And the deviation of the proportions is look like that. Okay, so this is a bunch of just notations. I believe I covered them all, but I might have missed something. If I did, I'll revisit it in a future slide. Now I want to spend some time just talking about the one var_stats in your calculator. Now you've had a lot of experience with this particular function in your calculator, okay? But just review some things. So I listed some data, 19 values there. Now if you were to type all those into your calculator into list 1, so hit stat edit, list 1, you can calculate the mean, median, mode by doing one var_stats, which is located under stat calc. Stat calc. Okay. Those are the buttons you would hit on your TI-83 calculator. Now if you have a 84 plus, it should still be the same, but if you have a Casio, it might be a little different. Okay, but I'll be talking about things with the TI-83 plus. Now you can use your calculator to find the mean, median, mode. Okay, the calculator one var_stats won't tell you the median or the mode, but you could sort the list in ascending order to find out these values as well. Okay, so if you go to stat edit, if you go to sort A, which stands for sort ascending, you just have to choose which list you want to sort, hit enter, and it says done, and then therefore you have a sorted list of data. Now make sure you only do that though if you're dealing with one column, because if you have two columns, if you sort one list, it may not adjust the other list as well. But to find the mean, you just look at the calculator value. So if you look at the one var_stats for this, you see the mean will say it's 14.736,84211. The median, sometimes denoted as x with a squiggle over it, which is a tilde. So that's a symbol that you might see for a median. The median or we could just say median, it's just going to be essentially the middle value of the data after it's being ordered. Now your calculator will actually tell you this, so if you hit the down arrows, you'll see MED is equal to, okay, and it says specifically that the median is 14. The mode, your calculator won't tell you, but it's essentially whatever occurs the most. You might have multiple modes, you might have no mode. Okay, so if every value occurs exactly the same amount of time, then there's no mode. If you have, so in this case we have 888, those occur 3 times, 14, 14, 14, but everything else occurs twice, once, or once. So in this case we have 2 modes, we have 8 and we have 14. Okay, now if we only had 2 14s, then it would be 8, okay, alone. Basically whatever appears the most. That's what the mode is. Now your calculator will also give you the standard deviation of your data. Now you have to be really careful about which one you're using. There's 2 standard deviations, the SX and the sigma S. As we just saw in the last slide, the SX refers to the sample deviation, which is the sample standard deviation, and the sigma refers to the population deviation, which is a population standard deviation. Sometimes you hear them referred to as just a deviation, but they're all standard deviations. Okay. Now, when to use each depends upon the problem. If you are told that you have the entire population, this is everyone that you could possibly survey from or everyone that you collected data from, then you're going to use this, the sigma x, because you know the population, therefore the deviation that you have is a deviation of the population. It's known. But the SX, the sample deviation, is used to account for the fact that you don't know every value in the population. So it's automatically going to be slightly larger than the population deviation, because remember, a standard deviation is just a measure of spread, how far away you are from the mean. So if you don't have every value in the population given to you from your sample, then you want to increase your spread a little bit to account for the fact that you don't have every value of the population. So in this particular example, the sample deviation is 7.60732180.4, and your population deviation is 7.4044233324. Okay. So notice the sample deviation is slightly larger. So if you are not told that you have the whole population, but you sampled from the population, or you surveyed part of the population, you use the sample deviation. And that's typically the one you're going to use. Okay. With all doubt, with all likelihood, you are going to be using the sample deviation. Now another thing your calculator will tell you in the one verse stats is the 5-number summary. And that 5-number summary is just the min, the first quartile, the median, the third quartile, and the max. Those numbers tell you how you're going to create a box and whiskers plot, which divides the data into 4 equal parts. And in this case, the min is 5, so you have to scroll down to see these. The first quartile is 8, the median is 14, the third quartile is 22, and the max is 30. So your 5-number summary is 5, 8, 14, 22, 30. Okay. It's a good idea to write down what those values represent, but if it says 5-number summary, you should list those numbers in that order. Now what that means is on your box plot, if you were to create a box plot, I'm going to go 0, 5, 10, 15, 20, 25, 30. Okay, space it out pretty easily. For your box plot, what you're going to do is you're going to, for each of these 5 values, create your box plot. So above the 5, I'm going to put a line. Above the 8, which is roughly about there, I'm going to put a line. Above 14, which is right there, I'm going to put a line. 22 is about there, and 30 is over here. To complete my box plot, I'm going to enclose the middle portion of my data, and then I'm going to draw whiskers to the end. Now some people on their box and whiskers, and this is perfectly acceptable, will put a little dot at the end. Okay. Both of these are completely acceptable ways of doing a box and whisker, so feel free to use either. But what this represents is it divides it into your data into quarters. So 1/4 of the data lies between here and here, in the first quartile. Another quarter of your data lies in the next little part of your box plot. Okay, and another quarter, another quarter. So notice what this is kind of interpreting is that there's more spread of the data in the upper end in this data set that I gave you. It's spread out more in the upper end, but it's more compact towards the lower end. Now another thing that you learned in this unit was something called the interquartile range. And that is found by just doing the third quartile minus the first quartile. So if you want to add this to your formula page, that would probably be a good idea. In this case, the interquartile range, which is the middle half of your data, centered around the median, the middle half of your data is going to be 22 minus 8, which is 14. Remember, ranges of value, it just tells you the distance from the lower part of your range to the upper part of your range. And this part right here is the interquartile range. Another big thing about the statistics unit was the normal distribution curve. Here's a graph that represents, in general, some easy percentages about the normal distribution. Now, notice a few things about the normal distribution is that it's symmetrical. It is symmetrical. Oh, went back. Oops, let me go back. Sorry about that. It is symmetrical. It is centered around the mean. Okay. And most of the data is within 1 standard deviation. In general, when you're dealing with inferential statistics, you want data values to be within 1 standard deviation in order to be able to conclude that the data you're looking at is part of the population. Okay? Anything beyond 1 deviation becomes much less likely. Okay? And in general, we saw that between -1 and +1, so within 1 deviation, there was roughly about 68.2% of the data. Between -2 and +2 deviations, so within 2 deviations from the mean, there was about 95% of the data. Okay. And within 3 deviations, you essentially have 99.8% of the data. Okay. Depending on which chart you have, I might say 99.7, 99.8 is generally what this one is indicating because we have 0.1 on the end and 0.1 on the other end. Okay. So essentially, a normally distributed set of data, almost all the data falls within 3 deviations of the mean. Now there are ways we can use our calculator to find out the percent between 2 values, or what's called area under the curve. Okay, and you could use your z-score chart. I'll show how to use that in a moment. But the easiest way, because you're not necessarily going to be given a z-score chart or this particular graph, is to use your calculator to do normal CDF. And there's 2 ways you can use normal CDF. The first way is using z-scores, and the second way is using the data values itself. If you want to say, for instance, what is the probability that your data lies between the z-scores of 1.73 and 2.75. Okay. So you want to know, well, what is the probability that data values lie between those 2 z-scores? Okay. So then what you're going to do is you're going to use normal CDF. And you're going to type in the minimum, which is 1.73 z-score, and the maximum 2.75. And you'll see in your calculator that will spit out a number that says 0.0388352804. Okay. Now what that's essentially saying, I'm going to erase some of this on the normal curve so I can illustrate what this is saying on the normal curve itself. that between 1.73, which lies about here-ish, and 2.75, which is here, between those two values is roughly about 3.9% of the data. That's what that's saying. Between those two z-scores, 3.9% of the data lies. Now you could use the normal CDF with data values. In that case, you have to indicate the mean. Now, if you have a TI-84 plus, if you do z-scores, z-min, z-max, you'll have to input a mean of 0 and a deviation of 1. Okay, because that's going to indicate this is what we're centered around. The deviation of 1 is what we're dealing with by default. Okay, but the TI-83 pluses, you don't have to worry about that. It automatically accounts for that. Normal CDF can be used with the min-max. So let's say I want to know what's the probability that a data value is going to be greater than or equal to 15. Okay. In order to do that, you need to know what the mean is. So let's say the mean ends up being 18, and the deviations is 1.58. So using this, we can use information. We can use normal CDF. We're going to put the lower value, which in this case, if we're doing greater than or equal to 15, the minimum value is going to be 15. Now for the maximum value, since you go into infinity, you can put some real large number. I like to put in 1E99. Okay, so the E, if you notice in your calculator, is on the comma button. You have the second comma. 1E99, that essentially represents positive infinity in your calculator. But again, you can put any really large number that's way outside of the range of values. And the mean is 18, and the deviation is 1.58. And that'll spill out a number. And in particular, it says 0.9712, so forth. Okay. So what this is saying is that 97.12% of the data is above or equal to the value of 15 if the mean is 18 and the deviation is 1.58. On the z-score chart, that means we have roughly about maybe here-ish and above. Because the mean is 18 and the data value is 15, way below there. Okay, so it's more than 2 deviations away. Or roughly about 2 deviations away. Alright, now let's look at finding z-scores. Now if you know the percentile that a data value lies, you can actually find the z-score for that data value. So let's say the value that is associated at the 24.5th percentile. So basically you're looking for the z-score 24.5% of the way in. Where does that end up? Okay, because percentiles, remember, always go from the left. Okay. So what you're going to do is you're going to use inverse norm, which is also in the same place as normal CDF, second distribution. And you're just going to type in the percentile as a decimal. So I'm going to put in 0.245. Now if you type that in, then it gives you negative 0.69 essentially. Okay. So your z-score is negative 0.69 associated with the 24.5th percentile. So that's roughly about here. So that's some words about the normal distribution curve. Let's move on to the next slide, the z-score charts. If you're asked to find the area using a z-score chart, now this is something you're going to have to do in a college level statistics course or any future stats courses you take, because most colleges use this chart to find the values or the probability between certain values. This first column represents the z-score to the nearest tenth, and then the column headers are just the hundredths place. So if I want to find the area associated, and this always tells you the area between the mean, whatever the mean is, let's use mu, okay, and whatever the z-score is. It's always going to give you to the positive z-score. Now, because it's symmetrical, you could also use it to find it for the negative z-score, because it'll be equal. But this will give you the positive z-score area. If you notice on the bottom right-hand part of your chart, it goes up to 0.5, which is half the area. Now, let's say I want to find the area associated with the z-score of 2.38. So what I'm going to do is I'm going to look at 2.3. Oh, let's do a different one because I didn't put that in this chart. Let's say 2.18. Okay. You're going to look at 2.1. You're going to look at this row. And you're going to look at the column for 0.08, because that's 2.18. And that zeroes in on this value right here. So what that tells you is that between the mean and that z-score of 2.18, that area, or that probability between the mean and that z-score, is that value, 0.4854. Or about 48.54%. Like I said, this also works for to the left of the mean, so negative z-scores. You just look at the same value, ignore the negative, but that would just give you the area there, as if it was on the other side. Now you have to be careful about using this chart with finding, for instance, the area where it's above a certain value, like above 1.8. Okay. In that case, looking at the z-score chart, that's a horrible curve. Draw this a little better. Looking at the z-score chart, it's going to give me the area between 0 and 1.8. Okay, so looking at 1.80, looking at here on the chart, 4641. But what I want is this right here. This is the part that's greater than 1.8. So what I have to do is I have to take into account that there's 50% of the data to the right of the mean, and I'm going to take away that 4641, because I don't want that area between the mean and the z-score. Doing that, we get 0.0339. So, or in other words, 3.39% in that little tail. Alright, that's how you read a z-score chart. So this is the end of this video. In the next video, we're going to focus on some inferential statistics, and I look forward to see you in that video. Thank you for watching this one.